First of all, I would like to thank organizer for inviting me to give a seminar talk at a seminar of my teacher, Vasily Исковskих. And today I'm planning to speak about the topic which I call stringy Euler numbers of toric Calabi-Yau hypersurfaces. So I will start. I would like to start with introduction to Euler numbers, stringy Euler numbers. And for this, I will probably choose additional commenter. Yes. So this is, yes, then I can better show. Yes. So I would like to start with reminding maybe well known for many people definitions, but nevertheless I need it because I want to remind definition of stringy Euler numbers. So we start with X to it's a normal quasi-projective Q Gorenstein algebraic variety, and consider arbitrary resolution, but not completely arbitrary. So we need, so a resolution will be denoted by rho, and the variety Y, which maps to X is smooth. It should have as exceptional locus a union of smooth irreducible divisors with only normal crossing. And I use I as an index set for divisors. So divisors are numbered from 1 to R. And write in this situation canonical class of non-singular variety Y as product of canonical class on X plus some rational linear combination of classes of exceptional divisors. So this is possible as soon as I mentioned at the beginning, I need Q Gorenstein property. So the canonical class on a singular variety, possibly singular variety X, should be Q Cartier divisor. So some multiple will be that Cartier divisor. And I will need some invariant depending on these coefficients AI. These coefficients AI are rational numbers, and we call them discrepancy of divisors of this exceptional divisor DI. So next, I remind that the three important type of singularities that we consider in algebraic geometry. Terminal singularities of X means that the discrepancies are positive, canonical, that these discrepancies are non-negative, and log terminal, the discrepancy coefficient should be greater than -1. And don't forget that these discrepancy coefficients are rational numbers. So now I come to first main definition. This is a definition of stringy Euler number of a singular algebraic variety X. So for this definition, I need that X is a Q Gorenstein variety. And then, so we take resolution rho as above, Y smooth variety, and exceptional divisors, they are normal crossing divisors. We have this equation relating to canonical classes X and Y. And then we also introduce some other subvarieties. They're indexed by subsets J in the set I. So for any finite subset J, also including empty set. So for empty set, there will be a separate definition. So for empty set, for any such subset, I define a closed subvariety, and it will be a smooth subvariety because of normal crossing condition. So for the subset empty subset, we take this subvariety by definition the whole smooth variety Y, and for any proper subset, it could probably equal to I, but not empty anymore. So we just intersect divisors with index J small in the subset J big. So these are subvarieties. And now, in order to define stringy Euler number of singular variety, we write down an expression. I write it into slightly different forms. Here is the first formula. Well, it doesn't have any alternating sums. So we remark that it's an expression which is a rational number. And this rational number depends on a summation over all subset J. And for any subset J, we take a usual Euler number of smooth variety, dj, and multiply it by some rational number.
So it depends only on the singularities, right? Is it written?
So the aj that depend on the singularity, but what could you repeat again? I hear not so good.
As for I understand, your formula, this expression depends only on the singularities. Not, for example, if variety is smooth, then is zero. Is it correct?
No. There is a chi of dj factor, which depends on the variety.
Sorry. I see.
So it's just a moment. This formula depends on the resolution. So I take any good resolution with normal crossing divisors. I write down this relation, and this relation determines coefficient AI. And then I use for definition Euler, stringy Euler number of singular variety, just these coefficients, and usual Euler number of this strata. So it's the closed subvarieties. If X is projective, then they are also projective. So, and they are, these numbers will be multiplied by such a product. The product runs over all indices in this subset J. So if it's not clear what, you can, I write it once in this form, and then I subtract one from this fraction, and I get this, but I get a number sign, and depending on the cardinality of J. So this is just a trivial transformation. Do you have any question to this formula?
No.
No, everything is clear. And moreover, probably
Can I ask a question?
Yes.
So the coefficients remind of cyclic coverings branched over these divisors. Do they have something to do with this?
I don't know. I cannot answer. So the coefficients AI, so they somehow measure change behavior of canonical class. So if the variety X is smooth, then definitely after resolution, the canonical class will have zeros along some exceptional divisors with some multiplicity, and this coefficient will be integer, positive integer. But we consider a more general situation, and then when x is not smooth, then first we need to multiply canonical class by some power such that it will be Cartier divisor. Then we take a pullback of this Cartier divisor and work with this pullback, comparing with the corresponding multiple of canonical class of y, and such we get a relation with integer coefficient, and then we divide by this index that we used to get a Cartier divisor. So, but I don't want to comment on some relation to some other. It's possible to see such kind of relation in many situations, and well, discrepancies there. There's some kind of measure of deviation from canonical class X, pullback of canonical class X and Y. And I will consider some examples for illustration of this this invariant. So first, just
one more question. Suppose we take a cone of elliptic curve.
Yes.
How does it look? Your formula?
So the formula looks in any situation the same. So this is so what you need to resolve singularity, yes, and you need to compute this this coefficient AI, and then substitute into formula.
Yeah, but in this case it's a -1.
You mean to write it
divisor over in the elliptic curve case?
Yes. So I forgot to say, I would like to definitely to assume that my X variety X has at worst log terminal singularities.
I see. Okay.
And then there will be no problem with this the division by. Probably you mean that we cannot divide by 0.
Yes.
Yes. No. I forgot to say. I considered only these classes so only variety with these classes of singularities. Not worse. Not even log canonical. So just the worst will be log terminal. The best will be terminal, and intermediate case canonical. And then all these sums in denominator will be positive, never we get 0, so everything is well defined. Is some more question? So this is a formula.
Yeah, the question is whether the Euler characteristic of X itself or Y itself participates.
Maybe I will answer your question. Let's.
Sorry, I already asked. It's first D empty set. Participate. It's empty set. So it should be Y.
Just a moment. There should be some. So, could you repeat again your question?
The question is whether there is a summand which is just the Euler characteristic of Y.
Yes, there will be a summand corresponding to empty set.
Okay.
So if you take an empty set, then the product will be 1. And you get just Euler number of Y Because it's exactly the case of empty set.
Okay, thank you.
Mm-hmm. So let's go to the next slide. So I would like to discuss some general properties of this number. So first of all, I would like to say that that's very important. This rational number, stringy Euler number, doesn't depend on the choice of the chosen desingularization. And in particular, if X is smooth, then we can do a stupid thing. We can resolve and blow up some, for example, smooth subvarieties on many times on a smooth variety. Again, we'll get to some resolution, formally speaking, but it doesn't influence on this number. Stringy Euler of X will be just a stringy Euler of usual Euler number of X. So it independence on the desingularization. This is fact not so evident, and actually this is the idea also behind the motivic integration, some kind of non-Archimedean integration. But I will give you some impression why it happens in some particular case when I take special varieties X and Y in some special resolution. You will see why it happens. So for the moment, just believe me, the result of this formula that we see on the previous slide, so this expression doesn't depend on the chosen resolution. So it will be well-defined invariant of a singular log terminal variety X. So next statement, it's easy to see. So if this resolution is discrepant, that means all discrepancy coefficients are 0 for all I, then the stringy Euler number of X will be exactly the usual Euler number of smooth variety Y. Let's look and see why it happens. This is why I wrote this second line. So if you in second line put all Aj to be 0, the only summand that will be survive and will be non-zero, it will be just corresponding to empty set. All non-empty product will be 0. So then we can ignore them. And you'll see that in this case, the stringy Euler number of X equals the usual Euler number of this discrepant resolution. And well, this is example of such a situation appear in surface theory when you have surface ED singularities, they are canonical singularities and double points, and you can resolve them in minimal way, and this minimal resolution will be exactly of this type. It will be discrepant resolution. So that means if you have a surface with canonical ADE singularities, then this stringy Euler number of such a singular surface equals the usual Euler number of its minimal desingularization. So another important thing from point of view of birational geometry says the following. If two varieties X and X prime are birational and not only birational, they are K equivalent, then stringy Euler number of X and stringy Euler number of X prime are the same. So such a situation happens usually, for example, if you have different minimal models of the same variety. In high dimension algebraic geometry, you cannot expect if minimum one exists, it can be not unique. So different minimum modes, for example, for three-folds, they are related by flops. They need not be non-singular. They may have singularities. And this is also important that we need some topological invariant that could be applied to singular varieties. So minimal model and minimum model program show that we cannot avoid work without on this singularities starting from dimensions v. So, but it is good invariant. It's good invariant from durational point of view. So next, what I would like to say, I'd like to write down another version of the same formula, but it uses a locally closed stratification. So please believe me that the first version actually equivalent to this one, but the difference is that we take the coefficient, not all the number of closed subvariety, but the local, but open strata. So we take from this closed subvariety all strata that coming from divisor that do not contain this subvariety. So we somehow deleted from this closed subvariety some proper subvarieties, and we get an open subset. This open subvariety has a natural mixed Hodge structure, and but for me it's only Euler number at the moment is important. So using additivity property, you can really, as exercise, rewrite the previous formula in new form, and then the summation will be of Euler number of this locally closed strata, but the factor will be much more simple. It will be just product of 1 divided by discrepancy plus 1. So this very simple expression. And I would like to explain why I need this second version of this formula for the stringy Euler number. I would like to illustrate this formula for toric varieties. So toric varieties, they are equivalent compactification of algebraic torus, and we need toric varieties with a property that it is Q-Gorenstein. So Q-Gorenstein toric variety, it's not, of course, it's defined by a Fn in some vector space, sigma is a Fn, but we need also some condition which says that there exists omega, some piecewise linear function, it's linear on each cone of the Fn, and it satisfies the condition that on every lattice generator of one-dimensional cone, I would denote it by EI, the value of this function is 1. So for any primitive generator of one-dimensional cone in this Fn. Why I take toric variety, that will have many reasons. Actually, it's for me, it's main illustrating example. It's somehow for me also was a motivation to even to define such an invariant, looking what happens with toric varieties. But another reason is that toric desingularization, that means this map rho y to x, can be chosen also in toric category. So this desingularization y is determined by some regular refinement sigma hat of, so that means every bad cone which is not generated by part of the basis should be subdivided into subcones which have this property, and we can get a new variety about this subdivision, which all divisors and this toric variety will be smooth, and we get probably more one-dimensional cones that used in this new Fn. I would denote this cone by tau j. So, and the generators of this cone by EJ. important is that we can write down the formula. So we need, of course, so we need this kind of formula. And this formula for toric resolution can be computed very, very explicitly in combinatorial. Namely, we need this coefficient, a discrepancy coefficient, and these discrepancy coefficients can be obtained by the following formula. It's just the value of this piecewise linear function. Not maybe I have to mention this piecewise linear function is possible for canonical class, and a sigma piecewise linearity of on each cone it's equivalent that we have. Was a question for me? Something like somebody has a question.
No, it hardly was a question. It was some just special effect.
Okay, so one can easily compute this discrepancy coefficient. So this discrepancy coefficient is the value of this function omega on this new, possibly new vector that we added, -1. And since this function omega is positive, so on the support of this fan, this number will be always strictly greater than -1. So don't forget that this value will be positive. And moreover, if you now apply the previous formula, this formula, second computing for string Euler number, you can immediately see that all strata that we have, there will be tori of different dimension. So the Euler number of this locally closed strata will be almost always almost anytime 0, except you have a 0-dimensional orbit. So that means you have a fixed point. So repeat again. So the Euler number of this strata will be 0 unless this subset will be of cardinality D. And this set that we get, it's a torus invariant fixed point, which is just intersection of D transversally intersecting toric divisors. So that means in this situation, the number will be 1. So that means the stringy Euler number of any Q-Gorenstein toric variety is just a sum over all maximal dimensional cones in the resolution, and you add just this product. Now it's important to analyze what is this product in fact. So let's look at locally. So consider just D-dimensional cone generated by a basis of a lattice, and consider linear function on the positive linear with positive values on this cone, and consider values of on generators EI. These are positive numbers. So then this product is nothing but just this product. And then you can easily see that this is nothing but a lattice normalized volume of D-dimensional rational simplex that we get by cutting this cone with this inequality condition. So maybe I have to draw a small picture. What we have? So we have a cone we have a function. So this is a function y, and it's equal to 1 at some. And we look at value of this function. So what I want to say that it's a volume of this area, but this volume will be computed just comparing with the standard simplex. Standard simplex will obtain when we take just the basis of our cone. But nobody says that this hyperplane goes through these points unless these values of this function on these generators, like this will be generator E1, and this will be E2. So this will be values of, sorry. And as soon as we know values, so we can just see that the level, one level hyperplane of this linear function omega cut from the cone some simplex, and this product is just volume of this simplex.
So the stringly Euler characteristic is nothing but the volume of spanning polytop of n polytop of the initial single toric variety. So the polytop whose vertices are rays, integral generators of rays of the initial toric variety. Am I right?
I would like, this is the local situation. So this is a polytope. In general, if you, I would like to say, in general, you need subdivision in such a codes which are denoted by a basis. And if you do it, and if you do this computation in each cone of this refinement, then you get a summation of all of maybe other part, and then there will be another cone, this part, and it will be more. You can cover by such a simplices a more complicated domain, and in fact, it will be if you look at the globally at the function omega and consider the compact subset where this function less than 1, then you get a compact in the no. If the assume that now we have not local situation, we take a projective variety and we have a fan, a complete fan, then this set will be compact, will be a polytope, some rational polytope. It will be not rational. It will be some it was not in the convex, but it will be some polyhedral compact subset with and all vertices will be integral because our function has at the beginning has values 1 on the generators of the original fan. So one can say if you have a fan and you marked for lattice generating lattice point on this fan, then you take just this compact subset. It need not be convex, but the volume of this compact subset is exactly the stringy Euler number of this toric variety. And it was. That's what I mean. This is what you mentioned, yeah.
Yeah, thank you.
And such a subset appeared in the paper of Miles Reed, published '83, decomposition of toric morphism, and it was called shed of the fan. So for any fan which admits piecewise linear, which comes from the Q factorial toric variety, there is some polyhedral domain, And by the way, this there is a polyhedral domain, and it's called shed of this fan. So let me delete this. There's a better editor. Otherwise, so let's go to the next slide. Yes, I took some examples. Yeah, log terminal singularity, which is a quotient singularity. So one example is very classical. We take just action of a cyclic group on C2, cyclic order n, and it acts like this. Zeta is a primitive root of unity, and K should be co-primed with n. So in this case, we get an action, and we consider the quotient. Quotient will be usually singular toric variety, affine toric variety, and one can see that the usual Euler number of this toric variety will be 1. So it even doesn't note the singularity, as if it were usual affine plane. But stringy Euler number is very sensible, so the corresponding stringy Euler number will be just the order of this cyclic group. That means will be n. Another example where we have some application, even some application of this invariant, we consider action of cyclic group of order 2 just by -1, and we get a quotient singularity. Of course, also in this case, one can easily see, and it's geometrically or just using idea that I mentioned, that in this case, the usual Euler number of quotient will be 1, but stringy will be 2. So the easy example. Now, what I want to say, and I will stress again, application to minimal model program. So minimal model program seeks for good representatives of a given birational class, if such a representative exists, and it's naturally to assume that such a representative has not so bad singularities, and this is how terminal or these canonical singularities appear. But singularities don't allow to use usual topological invariants like Euler number in a way that it has some good properties. As I mentioned, for example, minimal model of the same variety are not unique, and it could happen that different models have different usual Euler number, but stringy Euler number will be the same. So this is what I want to stress. So if two minimal models, minimal algebraic varieties are birational, then they have the same stringy Euler number. I don't claim that it's only one invariant. Actually, it's very, very it's a simplest invariant, which with this invariant, there are much more invariants that have such properties coming from Toeic integration. But this is a simplest one, and we can test, as we did it in the previous slide, for Toeic variety, and see this some kind of independence on the resolution. It's one compute volume, just different subdivision of the interesting polyhedral set as union of simplicities. But of course, volume will be the same, and then this somehow justifies this independence. Now, next, and that means that stringy Euler number is a well-defined function on the birational class of algebraic variety. So we can take any birational class and can ask what is the stringy Euler number of this class. That means stringy Euler number of any minimum model or even canonical model. So canonical model difference from minimum model by crescent morphism. So they are K equivalent. And then it's enough just to take a canonical model, any canonical model. That means variety with at worst canonical singularities. And then we obtain the same string invariant.
Sorry, do you mean varieties of general type, right?
No, it's not general type.
If you are talking about canonical model, for example, for Calabi-Yau, it is just a point.
Of course, canonical model, that means a model with at worst canonical singularities and effective canonical class. And Calabi-Yau is such a variety.
You mean that it's a, I see. Because traditional definition is just approach of canonical ring.
Yes, yes, but it's true that canonical model say in this one, in this way, but actually, if we have variety with non-negative codarian dimension, we can take also birational model with at worst canonical singularities. And then this birational model allows to get all information about pluricanonical ring, etc. So the canonical singularity.
Of course, I agree. Thank you.
Yes, and then in particular, we have this invariant for any canonical model, that means birational model with at worst canonical singularities, we have the same invariant. And this is stringy Euler numbers has such a property. It's very convenient.
Sorry, in another question, is it a new invariant? So more precisely, can it be expressed in terms of other invariants?
What other invariants you prefer? That depends.
Volume, you see, plurigenerar, you see, all the invariants of canonical rings.
Let's say, of course, for example, for surfaces, Euler number is related to square by Noether formula. You get a relation. So,
yes.
So there is a relation, but it's I don't want to. I want to consider it separately. So independent on other invariants. Of course, we can ask about other invariants which are the same for all canonical models like plurigenerar. But I think it's more complicated. So the stringy Euler number, it is very simple invariant. So you can test it to get a feeling. As I said, Toeic varieties give enough information and enough feeling of this invariant, and it's easier to compute. And of course, these invariants are not, can be applied not only to Toeic. So it's only illustration, like Riemann-Roch. Riemann-Roch, you can look at Toeic case, and it's a very interesting combinatorial statement, but it works for arbitrary algebraic varieties. So this is good. It's very good illustration, and I believe that other similar invariant can be also introduced and checked. But for me, this invariant will be the topic of the talk. So as I said, for case of surfaces, this invariant is just, for example, you take any case surface with ADE singularities, take the stringy Euler number, it will be always 24, as if it were smooth case surface. So this is the property. It gives an invariant, and it will be integral invariant for surfaces, but starting from threefolds, this invariant that I mentioned, it will not always be integer. It may have a rational value. So there are many birational classes of Calabi-Yau varieties, canonical and terminal and so on, with rational Euler number. But we discuss it later. So, and yeah, this is exactly what I mentioned the last remark. So if we know that a stringy Euler number of a given birational class of algebraic variety has non-integral value, then definitely we can guarantee there is no smooth minimal model in this class. So one should be, well, should definitely work with singularities, and the opposite is not true. For example, it could be algebraic variety which don't have a smooth minimal model and still have integral value of stringy Euler number, but nevertheless we have such a property. So, and what I also want to mention, it was observed in this famous paper of Miles Reed, 1983, that if we have, so for Toeic case, if we have two Toeic varieties X and prime, two projective Toeic, two Einstein Toeic varieties, such that the second variety X prime is obtained from X either from divisorial contraction or a Toeic flip, then the stringy Euler number will be strictly smaller. And don't forget that for Toeic varieties, this number is always positive integer, so for projective. So that means we have always termination of flips immediately by this invariant. It's of course it's not a complicated statement, but it's elegant and pleasant to have such a measure of complexity.
So it follows from your description of this stringy Euler characteristic as a volume of this polytop, yes?
Exactly. This is actually, yeah, exactly. It follows.
I'm sorry, but you said that this is a rational number. So how do you deduce termination?
No, for Toeic varieties, it will be always integer. As I said, it will be always integer because the polyhedral set that you volume to compute, it will consist of union of lattice polytopes. So remember, maybe I draw exactly picture. Even for
Okay,
this,
okay.
yes,
Fine. Mm-hmm.
Yes.
I understand.
So, in Toeic case, we are very lucky and we have a value integer, and then, but in general, it's not true. So what I want to say next, it will be the topic actually initiated by Askol Khovansky, and I would like to consider in Toeic varieties hypersurfaces. And in fact, this hypersurface intersecting with the torus orbit gives hypersurface, affine hypersurface in torus. It's defined by Laurent polynomial, and the important invariant of this Laurent polynomial is Newton polytope. So we now fix lattice rank D. We consider this lattice as a lattice of character of d-dimensional torus. And then we take Laurent polynomial, that means element of this ring. And we call that it's a non-degenerate polynomial if there exists projective torus embedding some smooth projective variety, such that the closure of this affine hypersurface defined by zero set of this Laurent polynomial is smooth, and it gives us together with toric divisors a normal crossing set of divisors on this projective smooth toric variety. So this is one of possible formulation of this non-degeneracy condition on Laurent polynomial, which I prefer here. But there are some other non-degeneracy condition in terms of this polytope, and one non-degeneracy condition is non-vanishing of so-called principal A determinant, which you can find in the book of Gelfand, Kapranov, and Zelevinsky. So this is a polynomial in coefficients of, and it vanished exactly when non-degeneracy condition violates. That means non-vanishing condition for a principal A determinant, where A, this is a set of monomials appearing in this Laurent polynomial. It's exactly the characterization of non-degeneracy of a Laurent polynomial. So we, but I prefer this geometrical characterization, that there is, that we can resolve singularities of hypersurfaces just by toric methods. Hamansky gave another definition, and then there is a theorem that in his definition there is a resolution, toric resolution of singularities. So, well, and also I would like to consider canonical Calabi-Yau varieties. So by canonical Calabi-Yau variety, I mean a normal projective variety in X, of course irreducible, with at worst canonical, Gorenstein canonical singularity. Gorenstein comes from the triviality of canonical class. So these two conditions that I demand from X, the canonical class should be trivial, and some vanishing condition for structure shift. It's usual condition for Calabi-Yau. But I'd assume that X need not to be smooth. It's enough to have at worst canonical singularities. Then in this case, it will be Gorenstein canonical singularities. So this is another definition I need. Well, and now I would like to mention, there was a paper of mine, 2017, where I investigated the following two questions. First question was how to characterize a lattice polytope delta such that non-degenerate hypersurfaces with a Newton polytope delta are birational to canonical Calabi-Yau varieties. It's what one question, just to find criterion, combinatorial criterion for delta. And second was how to compute the stringy Euler number of this Calabi-Yau variety, canonical Calabi-Yau, by combinatorial formula using just polytope delta. So both questions received complete answer. So there is a criterion for a lattice polytope delta such that corresponding non-degenerate hypersurface is birational to a canonical Calabi-Yau. And there is an explicit combinatorial formula based on the polytope delta such that you can produce with this formula the stringy Euler number. You can take different polyhedra satisfying the first condition and check what we get. Sometimes you get something nice, sometimes not. I will mention in my talk later some results. So these are two questions actually has a motivation. The motivation comes from mirror symmetry. And I would like to mention mirror symmetry. Yeah.
So in the first question, it depends only on the polytope. So if we have two non-degenerate hypersurfaces and one is birational to canonical Calabi-Yau, another one should be birational to maybe another, but also Calabi-Yau, is it?
Exactly, exactly. I would like to I would like answer just as condition on polytope. So that means I can take one non-generic hypersurface. This for this polytope I get a closure and some birational model, projective birational, which is Calabi-Yau. I take another non-degenerate, it will be the same property. Yes, so actually I will get a family of such Calabi-Yau varieties. But as soon as non-degeneracy condition is satisfied, so this should be birational to Calabi-Yau. So this is a first actually question problem. And the second, as I said, there is some invariant, very natural invariant, and some experience with Toeic geometry shows that it's possible to, and it's natural to expect there is such a formula. And now I would like to go to direction to mirror symmetry, and then at the same time some results. So let's consider some class of lattice polytope. So we call the d-dimensional lattice polytope is called canonical Phonopolytope. If it contains, lattice polytope means that all vertices are lattice points. If it contains exactly one lattice point in its interior. And for simplicity, we can always assume that this point is 0. So if not, we just move, make a shift and make shift an origin such that this point will be origin. It's convenient.
Is it assumed to be convex?
Polytope convex, yes, this is delta. Now delta is convex polytope. So it's a convex hull of finitely many lattice points. And we call this polytope canonical Phonopolytope if it contains exactly one point in its interior. So the easiest examples, I don't know, should I? Maybe we'll discuss that later. So it's easy to find such example. For example, in dimension 1, it will be like segment -1, 1. It will be such a polytope. It's lattice polytope with 2 vertices, -1 and 1, and exactly one interior lattice point is 0. And it's a single possibility for canonical polytopes of dimension 1. But for high dimension, it's much more complicated. So why one says that it's canonical Phonopolytope, that to actually a theorem. Why we are interested in such a class of polytopes? Because of very famous result of Chovansky, who gave a way to compute geometric genius of any non-degenerate toric hypersurface. Actually, you can ask, so geometric genius, it's a birational invariant. So of course, these hypersurfaces are fine, but you can take any non-singular projective module and take the dimension of the global section of canonical class, and it will be exactly geometric genius. And it doesn't depend on the choice of birational model. So it's like first component of the pluricanonical ring. So zero first component. So that is a birational invariant, and this birational invariant is possible to compute just from polytope. It's a number of integral point, lattice points in the interior of the polytope. And if we are interested, I say, Calabi-Yau varieties have a geometric genius 1. There is a nowhere vanishing differential form of top degree and only 1. This is the basis of this space. So we have this condition for Calabi-Yau, and this is how we can characterize canonical Phonopolytope. It's so a lattice polytope delta is a Phonopolytope, is canonical Phonopolytope, even only if the corresponding non-degenerate non-degenerate hypersurface with the this affine hypersurface has geometric genus 1. So this is how we can come to this condition. Another way to come to this definition, it turns out that there exists a natural bijection between d-dimensional canonical Phonopolytops and consider up to automorphism of d-dimensional lattice and d-dimensional Q-Gorenstein Toeic varieties. So it's a variety which is defined by fan over faces of this polytope. Usually, if you there are two possibilities to create actually standard way to get toric variety from polytope. You can take a normal fan, but in this situation, you take a fan in the same space where you have a polytope. So you get polytope with one interior. You have a polytope, canonical Phonopolytope with the interior lattice point 0, and then you take cones over all with this vertex, this 0, over all faces, and you get a fan in the same space, in the space of the polytope. So a little bit unusual, but for canonical Phonopolytopes we can do it, and we get Q-Gorenstein Toeic variety, even only if that means what at worst canonical singularity, even only if the polytope delta was canonical. So actually there are two ways of looking at the same object. So the lattice polytope with only one interior lattice point in interior. There is one way of thinking. We take this lattice as lattice of monomials. And there is another thinking, we take the same lattice as a lattice in the dual space of lattice of one parameter subgroups or lattice of the invariant valuation. So formally speaking, from Toeic point of view, terminology of Toeic geometry, this is a M lattice and this is a N lattice. But the same combinatorial object, the same combinatorial object. And this is how I would like to prefer to approach mirror symmetry. So mirror symmetry, it's not identification of one complicated object or category with another complicated object, another category. It's just two ways of looking at the same object, combinatorial object. So we have a canonical Phonopolytope. We can look at this polytope as Newton polytope of Laurent polynomial equation, or we can take this, use this polytope to construct some Toeic Fano variety. And of course, between this interplay, mirror symmetry actually appears. This 2 point of view on the same object. Let me say some words about results concerning canonical Phonopolytopes. As I said, I didn't say about this. So there is a theorem, combinatorial theorem, not complicated but important. In any fixed dimension D, there exist only finitely many d-dimensional canonical Phonopolytopes up to GL, up to an isomorphism of the lattice, GL. So that means it makes sense to consider the problem of classification of canonical Phonopolytopes, but with the increasing the dimension, the number of such classes of classes grows very, very rapidly. So as I said, in dimension 1, we have only one canonical Phonopolytope. It's a segment -1, 1. In dimension 2, there are 16 canonical Phonopolytopes. If you on the web, just go, you get this list of all these canonical Phonopolytopes, lattice polytopes with only one interior lattice point, up to GL2 isomorphism. And next case, three-dimensional case, has been classified by Alexander Kaspershik in 2010. And there you see 674,688 different three-dimensional canonical polytopes. Huge amount of such polytopes. And starting from dimension 4, so the complete classification list of all four-dimensional canonical Phonopolytops is still unknown. There are some results for special kind of this polytope, but in general it remains an open condition. Now I would like to restrict my class of canonical polytope to some subclass. And this is subclass has very nice duality. The subclass is called class of reflexive polytopes. So important that we have some nice duality. So combinatorial duality that I would like to discuss is based on, first of all, on duality between lattices. So we take N to be due lattice to M, is and corresponding to vector spaces due to each other, and the pairing between two lattices. So a d-dimensional canonical Phonopolytope is called reflexive if the polar polytope, and now let me stop at this in a moment. So this is the definition of the polydual polytope. We take all points, so the original polytope will the space M space, but the dual polytope in the dual lives in the dual space. It consists of all covectors or elements of dual space such that the scale product is greater than -1 for all points in delta. So informally, one can say the following. So, and it should be again a canonical Phonopolytope. Don't forget, canonical Phonopolytope means automatically it should be a lattice polytope. So that means this dual polytope should have lattice vertices. And that means that integral distance between, so we get a polytope, and the integral distance between faces of facet, we could mention one facet of this polytope delta has value 1. So this integral distance 1. So this is a that means if we take a normal vector to each facet of this inner pointing normal vectors, then this normal vector is exactly the set of vertices of dual polytope. Of course, in order to see this definition more informally, one needs examples. And as example, I would say there are examples of this duality polytope and dual polytope in dimension 2, because we can draw a picture. For example, if you take just a moment, I take polytope like convex hull of the base, like this. Yeah. So it's a basis, but basic vector, and this is -1, -1. It's will be a reflexive polytope, and the dual reflexive will be again triangle. So triangle. So it will be Newton polytope of a general cubic. So you can see that this phase, the inner normal, it's exactly this vector. The inner normal here, it's exactly this vector. Inner normal to this, it's exactly this vector. So it's there is a of course, here's a polytope, and the dual polytope has have this in dimension 2, they have the same combinatorial type. But starting from dimension 3, they have usually different combinatorial type. For example, there is a octahedron. So it's, and there is just a cube, U, and there are, so that's polytope. Here it's a dual polytope. This is convex hull of vector standard basis and minus vectors, so 8 points. If you write down dual polytope, you get equation, so all points in that coordinate are in between -1 and 1. So actually it will be this cube will be product of one-dimensional reflexive polytope with itself 3 times. So important is that if we have reflexive polytope, then the dual polytope is also reflexive. And if we have an evolution, so if you apply two times this dualization, we'll come back to this original lattice polytope. And this duality turned out to be very good for mirror symmetry. And moreover, I would like to mention there is one-to-one correspondence between k-dimensional lattice facet of delta and complementary dimension t star. So the sum of dimension should be d-1. So to each face of one polytope, there is a face of dual polytope. It's like duality. If you take, you can see this duality even on example of cube and octahedron. So there is duality. So let me now go to the next slide. So next slide, I would like to, yeah. Well, important is that there is a mirror symmetry for Calabi-Yau varieties. And it turns out that for each reflexive polytope, the corresponding non-degenerate hypersurface with Newton polytope, reflexive polytope, gives a family of canonical Calabi-Yau varieties. And the same happens also for dual reflexive polytope. Well, the general mirror symmetry predicts this kind of relation between Hodge numbers of Calabi, in smooth case, when you have Calabi-Yau V3 default and dual and the mirror symmetric. So there is some relation between Hodge numbers, and it holds for all PQ in between 0 and D. And this relation for Hodge number implies more weaker relation. It relates Euler number of V and V star dual varieties. So they are different by -1 to the power dimension of the variety. In this case, it's D. So if you have the 2D-dimensional Calabi-Yau varieties, then it will be D. So now, okay, and now I would like to mention an interesting formula that was observed long time ago with Dimitrios Dice. So it's result 94. My joint result with him. So if we consider delta to be a d-dimensional reflexive polytope, as first in my other paper, it was proved that in this case you get a family of Calabi-Yau varieties. And the canonical Calabi-Yau varieties, they actually hypersurface in the Toeic varieties, Gorenstein Toeic varieties, the Gorenstein Toeic Fano variety. So we don't need much work to get this Gorenstein canonical model. And then we can ask about stringy Euler number of this model. And it turns out that this can be computed by explicit formula. And this explicit formula is a summation over phases of theta of delta of different dimension, but between 1 and d minus 2. And here we take a volume, so integral volume of this lattice polytope times integral volume of another lattice polytope, but it's a face of a dual polytope. Here's there is a sign, minus 1 to the power k minus 1. And this is the formula. So we can apply this formula for X Calabi-Yau hypersurface in Gorenstein toric Fano variety corresponding to this polytope. And we can apply it for dual polytope, the star must be here, and for another Calabi-Yau family coming from the dual polytope. And from this formula that we have just for one case, we immediately see that this duality for all the number will be satisfied. But of course, exactly, stringy.
Yes. One question, sorry.
Yes.
I thought it needs some k factorial or some factorial in front of each of these. Isn't it right?
Yes. When I say volume, I mean that standard simplex spanned by basis should have volume 1. Standard lattice simplex.
I see. Yes.
And then, of course, otherwise it should be a rational number. But this volume, that means we multiply by factorial, of course. So it's usual technique in connection to lattice polytopes. We work with, we don't work with usual value, but for lattice polytope, it's much more convenient to get invariant. So, like degree of projective variety in Hilbert polynomial, the top coefficient you should multiply by factorial to get something reasonable, like degree of subvariety.
Thank you.
Yes, yes, you are right. I should mention that it's not usual volume, but multiplied by, here's by k factorial, here's d minus 1. Factorial, then you get. And by the way, I can explain why it happens. It turns out that if you have a variety x in a toric variety associated with a polytope, you get a stratification of this variety by faces of the polytope. And then in order to compute, you need somehow consider all the number of each strata, and it's responsible for all the number in k-dimensional strata. There is a formula of Khovansky which expresses all the number. It will be this sign times this. And there is another volume. It comes from the stringy resolution of singularities. As I said, it's a volume of some polytope, but in the dual space. So usually in order to compute stringy Euler number, you work with a space where you have a fan. In this space, you take also volumes. So this combination of two, you combine information from one lattice and from the dual lattice. And then you get nice equality. It turns out you can also, in this case, define not only Euler number, you can define even stringy Hodge numbers, and they satisfy the expected duality, as I mentioned at the beginning, in connection to mirror symmetry. Yes. Now, I would like to discuss not this case already long time ago, almost 25, more than 25 years ago. But now I'd like to discuss another topic, and it also started even earlier. And I would like to consider Calabi-Yau hypersurfaces in weighted projective space. Because physicists, when they started to work with Calabi-Yau varieties, they even at the beginning didn't know about toric geometry. It came later after they saw this mirror construction. But they worked with Calabi-Yau hypersurface in weighted projective space. And for me, it will be important some special case of hypersurfaces, Calabi-Yau hypersurface in weighted projective space. They will be defined by weighted homogeneous polynomial in d+1 variables. And the degree of this polynomial should be, this degree W, will be sum of all weights of this weighted projective space. Well, but there is one condition with, that allows to apply physical models, which they call Landau-Ginzburg models. This condition is called quasi smoothness. So we we want to consider hypersurfaces that not only define something good variety, but this should be varieties embedded in quasi smooth ways. That means if we take partial derivatives of this weighted homogeneous polynomial W big, partial derivative with respect to all homogeneous coordinates Zi, then this should form in the polynomial ring a regular sequence. This is a if you fix weights, for some weights you can find such a polynomial. For some weights not, and it turns out that there is only in every dimension there is only finitely many possibility for good weights. They were investigated, and each such possibility gives, from physical point of view, very good object, superconformal filtering based on Landau-Ginzburg potential, and this potential it will be defined by W. And at the same time, they can compute some numbers that mathematicians understood later that this have some mathematical meaning. But for physicists, they say that can be considered as analogs of Euler number or Hodge numbers of smooth projective algebraic varieties. And in this connection, I would like to mention a work of Waffa, 89, who produced a formula for computing this invariant. So I would like to remark that there is an intersection of these two situations for special case. Sometimes weighted projective space will be Gorenstein. It always Q Gorenstein, but Gorenstein, it's an additional condition for weighted projective space. And it happens if and only if this weights Wi, each weight divides this their sum, W small. So this divisibility condition implies in particular that we can choose a particular potential in the Fermat form. This is sum of power of homogeneous coordinates. This is our powers, positive integer powers. And then it will be automatically, this condition will be satisfied. Partial derivative, they will form a regular sequence in this polynomial ring. So it will be quasi-smooth. So this polynomial defines quasi-smooth Calabi-Yau hypersurface as soon as you have, on the other hand, this condition, W sum, and another condition, divisibility condition. And you can make an elementary number theory exercise that this condition together with divisibility condition in each fixed dimension has only finitely many Diophantine solutions. There is only finitely many tuples, integral positive tuples of fixed length D satisfying this condition and divisibility condition. So it's another kind of finiteness condition that I would like to mention. And of course, physicists found the complete list in low dimension of all these possibilities for weighted projective spaces. So let me say, but this condition, visibility condition, need not be in general fulfilled. So that means there are some much more possible quasi-smooth condition sometimes holds when the visibility condition is not satisfied. So we cannot choose this potential or superpotential in this form, Fermat form, but there is another way of choosing with more monomials or some other choice of monomials. And there are some classification results of this. So the first known classification result, it's a list of 95 families of quasi-smooth Calabi-Yau two-folds, that means characteristics in weighted projective three space obtained by Miles Reed about 1709. Then there was work of different mainly physicists and mainly the best results were obtained by Kreutz and Skarke. For example, in their paper 98, they found all families of quasi-smooth Calabi-Yau three-folds. There will be 7,555 families. That means there are so many possibilities for these weights, such that there exist quasi-smooth Calabi-Yau variety of degree equals sum of these weights and with such weights. And another result I would like to mention, physicists, maybe it's was not so rigorous, but Linker, Schimrink, and Wiskirchen, already in 98, they produced a list of 1,100,055 families of quasi-smooth Calabi-Yau four-folds, so four-folds. And this list was mathematically independently justified by Brown and Kasperschik in 2015. So I think the algorithm that now to produce more family, maybe it's possible to do maybe next dimension 5. But let me explain why this example is interesting for me. So then, as I said, in this case, we actually everything make dependent on these weights. So finiteness of the weights or invariant can be computed from using weights. And there is a formula that physicists used. It's called Waffer formula. So with this formula, he produced his Euler number, which later was understood by mathematicians as a all-before Euler number. And that Euler number here wrote as number theoretical expression. So 1 divided by W, and then there is a summation, maybe at first rather complicated, but it's nothing complicated. You can make a program which does this computation. And Qi, there are some expressions just which are opposite to W divided by Wi. Why it's so, they have some meaning it's called charge in the physical theory. And the formula looks as follows. So when we know that W divided Wi for OI, that means Fermat case, that then this number, the opposite, there will be always integer, and one can divide it by W, but it is not far from integer, actually. And we can see that elementary that you get integer. But if it's not Fermat case, it's not clear why we have by this formula integer. But in all cases, this is a fact, and there is a mathematical explanation of this fact. And this mathematical explanation was obtained by Ono and Ron, 93. So they, it was first approach to orbifold Euler number. So they considered a sphere, a real sphere, odd dimensional real sphere in this punctured affine space. It's a sphere around 0. And then one considers smooth compact real manifold, which is intersection of the our complex hypersurface with this sphere, which is also rather typical, for example, in singularity theory. And then we get circle fibration, C1 fibration of this hypersurface in a sphere over weighted projective hypersurface. So it's Hopf fibration, in this case will be Seifert fibration. And so we get a fibration with action of a circle. And we can and we work not with this variety, but with this real analytic variety together with action of a compact group. So what they proved is following. As soon as you have a quasi-smooth Calabi-Yau hypersurface, and you get a fibration of this hypersurface, of this real variety, and hypersurface should have degree W, sum of degrees of coordinates, homogeneous coordinates, then you can compute two equivariant K groups, K0 and K1. So K0 will be responsible for even cohomology, K1 for odd cohomology. So you subtract from this, and what you get exactly what formula of Waffa says. So in particular, since it's a difference of two integers, it will be always integer. So a priori, it's not clear why it's so, but this is one possible explanation. Of course, this series of first steps will be developed, and maybe the best way to mention and to say there is a theory of orbifold cohomology. Chen Ron developed this, and one can prove, one can compute not only orbifold Euler number, but can compute orbifold Hodge numbers, etc. So, and one can justify also all other prediction of Waffa, not only for Euler number, but also for Hodge numbers. Well, it's okay. But now I would like to say what will be mirrors of this Calabi-Yau. And it turns out that there is a good candidate for mirror. It comes from another idea. Also, Waffa is a co-author. This idea, it's usually called a Hori-Waffa mirror construction. And it was applied not actually designed for hypersurface, but actually for mainly for weighted projective space itself. So I would like to explain this polynomial. So we should consider algebraic d-dimensional torus. So, and this torus will be subtorus in the split standard torus with of dimension d+1, and it's defined by vanishing of some character. So this character is a product of coordinate variables to the power wi and product and equals 1. So we can consider it as a this torus, a d-dimensional torus, subtorus, which is a kernel of this special character, and this character depends exactly on the weight of weights wi. So in other words, we get a lattice of characters which defines a lattice of this torus. So there is a free lattice of rank d+1. They correspond to this torus of the dimension d+1. And there is a character, and well, actually a lattice of vectors, and we'd like to, of course, one should do so you can see that the arrow a little bit opposite. No, it's in the correct direction. So if you have an embedding of torus in this standard torus, for the characters you have opposite morpheme that is exactly corresponding. And the kernel will be generated by lattice vector. It sends one. This morpheme sends one to this lattice vector. No, everything is okay. So you get the coordinates xi as a standard basis of standard characters base of this torus c star to the power d+1, and one considers a very simple linear function, sum of all coordinates. It's a regular function. Of course, on this d+1 dimensional torus, very elementary, but we're restricted on the subtorus. And then it will be a Laurent polynomial. Laurent polynomial, depending, of course, on our vector of weights. For simplicity, I write it in this way. So in this Laurent polynomial, I call Horry-Buffer polynomial for weighted projective space with these weights. We can look at some examples of these Horry-Buffer polynomials. Especially it's convenient to illustrate with a case when one of weights, for example, is 1. So as soon as we have this condition, we can split this sequence such that we can look. So splitting, so you can just projecting on this first coordinate, I define a splitting, and we can consider a restriction of characters of the ambient torus and obtain characters corresponding to lattice vectors. So we get one standard basis, and then one more vector. It's exactly correct. It will be minus W1 minus WD. So we get a Laurent polynomial of this type. Maybe at this case, at this place, it should be mentioned, not special, very special case. Assume that all weights are 1. Then in this case, we get a well-known Laurent polynomial of this type, and for usual d-dimensional projective space. And this Laurent polynomial describes one logarithmic mirror of projective space. So this is how this polynomial appear. Now we can say more generally, we get a Newton the Newton polytope of Landau of Horry-Buffer polynomial. It's actually is a lattice simplex, and this lattice simplex with lattice vertices correspond. We number this. We'll use notation V0, V1, Vd for these vertices. They generate the lattice. And moreover, they satisfy the unique relation. It's the sum of WIVI is 0. So this is another description, and it's a unique description of the simplex that we get. It will be simplex Newton polytope of Horry-Buffer polynomial. So this it's obviously to see that this polynomial contains 0 in its interior. Well, and it's also very easy to see that this polynomial, Laurent polynomial, will be non-degenerate. So it's very similar to Fermat polynomial. Now next. Next, I would like to mention the result of myself and Karen Schaller. It will be it will appear on arXiv very soon. So this result says the following: assume that you have a sequence of positive integers of weights such that there exists a quasi-smooth Calabi-Yau hypersurface of degree of this W into this weighted projective space, and it's quasi-smooth. Then one can show that the affine hypersurface defined by Laurent polynomial of Corey-Waffer is B-rational to D-1 dimensional Calabi-Yau variety. I would denote it by X W star. And moreover, in the stringy Euler number of this Calabi-Yau variety corresponding to this simplex is -1 to the power D-1, the same what appeared in the Waffer formula. So this is up to this sign. It's exactly what appeared in the Waffer formula. Why I think it's important? Because in fact, this supports natural conjecture. So assume that a weighted projective space with this weight contains a quasi-smooth Calabi-Yau hypersurface of degree of this sum of degrees of variables. Then the affine hypersurface that used Corey-Waffer in the construction of mirror of weighted projective space is B-rational to a mirror. Well, this is a statement, but it's not only this what I want. Of course, what we have here, it's a justification, this statement on the level of Euler number, stringy Euler number, or Oberford Euler number. But there is something more what I wanted to say. There are some examples showing that, in fact, you can drop this quasi-smooth condition. And this actually two examples were given us by Harald Skarke. One example, it has appeared already more than 20 years ago in his paper with Max Kreutzer. So consider hypersurface of degree 43 in this weighted projective space. So if you sum of this weight, you get 43. What we can one can show that, in fact, the Newton polytope of this hypersurface, it will be a reflexive polytope. So by some other results that I mentioned, the corresponding hypersurface is B-rational to a smooth Calabi-Yau frequency, and you can compute Hodge numbers of this Calabi-Yau frequency. It will be 21 and 273. So the Euler number will be double difference, so it will be minus 504. But on the other hand, you can apply, it's one of the results of my paper with Karen, you can apply some formula which allows to compute stringy Euler number of Calabi-Yau compactification of this affine hypersurface in the torus defined by this equation. It is B-rational to also to three-dimensional Calabi-Yau variety, denoted by some also star, but the stringy Euler number will be different. So will be not it will be not 504. It will be actually 506. So the one sees that this expected test wouldn't satisfy, and that means the correspond. So with this equation, we cannot expect to find a mirror of variety that we can, for example, obtain by method of duality for reflexive polytopes. So that means quasi smoothness actually cannot be dropped, and there is even much worse example suggested by Harald Skarka. So we take a more simple example, hypersurface of degree 13 in 1,1,1,2,4,5 weighted projective space, and it's also not quasi-smooth. One can prove it. So it's not a list of quasi-smooth varieties, but one can show that this equation, Hori-Waffer polynomial, it defines a fine hypersurface which is birational to three-dimensional canonical Calabi-Yau variety. We can compute Stringy Euler number, and we get not integer. It will be rational. That means the minimal model of this Calabi-Yau variety will have singularities, and even not so simple singularities. Of course, there will be ADE singularities, but there is a paper of Dice and Rosen. They computed Stringy Euler numbers of all these kind of singularities. So I believe that this singularity appear on a minimal model, but the formula for there is a combinatorial formula for computing the Stringy Euler number, and it gives a rational number for this three-dimensional Calabi-Yau variety corresponding to the lattice polytope, the lattice simplex. So I think I finished what I wanted to explain to say today. Please, if there are some questions, my talk, of course, is over 1.5 hour, but there is a lot to explain, and so, sorry, I'm expecting. So I want to stop. Thank you.
Okay.
I have a question. So you consider Calabi-Yau hypersurfaces, yes? Do you have an idea or generalization for Calabi-Yau complete intersections?
I think already hypersurface case is not completely understood. So my long-standing problem for me was to try to unify all known mirror symmetry construction in hypersurface case, and still I cannot do it even with hypersurface case. So that means, of course, I expect maybe it's possible to do also for complete intersection, and definitely something can be done. But already hypersurface case doesn't have good clearance for me. So I think one should do more experiments, especially with, I didn't mention this, but there are some tests, some experiments with lattice polytopes, which are not reflexive, but still they produce Calabi-Yau varieties, and then to try to see how to probably to connect all possible mirror construction and results in a good way. At the moment, the mirror construction that I mentioned, for example, this construction with motivated by this result, this mirror construction, when you take mirror of generic hypersurface of degree W in a weighted projective space, and you take just one element, actually this polynomial, you can deform this polynomial definitely, at least in one parameter deformation is very natural, but more possibility. But there is one example, just particular point. It's like a Fermat point on a mirror. Such a Fermat point there exists in general on original variety. Not it doesn't exist on the original variety. And then, well, if you look and compare mirror construction coming from polytope from reflexive polytope and duality for reflexive polytope. And this kind of mirror construction, they're different. So they don't coincide unless you have a Fermat case. That means you have divisibility of weight by all particular weights Wi. In Fermat case, they agree, but not in non-Fermat. It's another construction. They not very orthogonal. So the common is that the mirror will be hypersurface in the dual torus. So there is a duality for tori. So there is a T-duality there. But this is not enough. I'm not satisfied only over this. It should be more. And there are some attempts, for example, suggested by Mavlutov. I also was very impressed, and I hope that it will be good extension and which connect many contractions. But then I found counterexample, and it doesn't work always. So sometimes it works, sometimes not. So already hypersurface case for me is unclear.
Thanks. And another question. So you discussed here correspondence between two mirror dual Calabi-Yau varieties, yes? And can you say something about Phonopolytops correspondence?
No, I'm not prepared to say something about it. I would like to, so maybe it makes sense to consider, but at the moment I cannot say. So for me, Calabi-Yau maybe have more primary interest than just Phono. This was motivation from very beginning for me. Of course, mirror of Phono varieties and Phono varieties are related to this, but and we see this exactly in this situation, but I cannot say much about this. I know that on the, using hypergeometric function, there are many results, and probably one can even justify something of this mirror symmetry for quasi-smooth Calabi-Yau hypersurfaces.
Thank you.
I have a question. Actually, it was in the beginning. Suppose you want to apply your invariant for termination of flips. What do you need for this? You have, of course, you have equality. It's strict, but your you have denominators. So
yes, I think it's a good question to ask, but I'm not sure that on this way you really get better results than other maybe with some other method, because look at three-dimensional case. There is a Shakurov termination of flips. Of course, in his arguments he used also discrepancies. So maybe in some implicit way one can rewrite it and show that it implies, and actually it should be for toric case, for toric morphism, it's true. But for arbitrary flips, why stringy Euler number will be strictly less than after flip? Even this is not obvious. maybe it's possible. Maybe it's good student topic. And maybe it's even not so easy for student as a student topic. I don't know. It's not clear. I think arguments of Hakoon, they're more they're simpler. And then if in three-dimensional case it doesn't work, so I don't see advantages. I cannot say that it might be good invariant to get termination of flips in this way.
See, but possibly you can use it with together with other invariants.
Maybe.
High dimension, you of course this is the same inequalities. If you want to apply Shakur's argument, it's not enough. Maybe some additional thing. I don't know.
Maybe it's possible. Of course, it's possible. Yes.
Okay, thanks. So,
Should stop.
no more questions?
Yeah.
Thank you.
Okay. Thank you.